Alright, so everyone's been asking for like a detailed overview of how the Mass Spec facility works. So let's start at the heart, I guess is like the blood of the Mass Spec facility. It is nitrogen gas. I make nitrogen gas by bleeding headspace gas off of liquid nitrogen tanks. That's how much I need. You can see for the Thanksgiving holiday I got a pretty good stockpile of these 350 PSI massive tanks on rollers here. Here's LCMS QDA stack, all right? So the point of a low-res system like this is it's called a single quad detector. So this is a quadrupole, no time of flight. So low resolution, but it can still multiply charge things to fit into its quad range. And so I can go into the detail on how quadrupoles work, but essentially this is just a single quadrupole. It's super small, still has a vacuum pump, and then it has a regular UPLC stack. So this is a regular UPLC, so ultra high pressure HPLC, right? And so this is a column manager that has about 8 columns in it. We have an extra column heater here. This is the sample organizer where you put your samples, and then we have a QSM pump. The difference between a QSM pump and like a BSM pump is the QSM you can blend all 4 solvents together. So you have low pressure blending instead of high pressure blending. So you're bringing in the solvents, you're mixing the solvents, then you're pressurizing it. And so they have high pressure systems as well, where you can. So it's like how fast you want to deliver your gradient accurately. So the kind of the cheapest way to do it is with low pressure blending on a quaternary solvent manager. And then on these systems, we usually have acetonitrile as our organic, or methanol isopropanol as slightly more nonpolar organic, and then we'll have formic acid water, and then usually some sort of neutral or high pH water. These systems are set up for students to run them themselves. So there's stock methods that we've created up at the top of every sample list that kind of give you an idea of all the different columns and all the different things you can do on the instrument. So it's pretty easy to get started. You can just get your samples to the right concentration. You can see everyone's just kind of running it in order here. And choose a method. Most popular method over here is just C18 separation in 5 minutes, or direct injection, just sending your samples right into the Mass Spec. And then on these instruments we have fluorescence detectors and PDAs and different absorbance detectors, so you can get that information. Instruments right here. This is the newer one. This is called TQ Absolute Triple Quad, and then this is the old Quattro Premier Triple Quad. So let's say you've run things on your single quad instrument. You have one single quad, right? You've been able to find the molecule you're interested in. You're like, okay, my sample prep is good. My chromatography is good. I got my peak. Now I want to do quantitative work. So many people ask me about quantitative work. These are the types of instruments you would do quantitation on. These are called triple quads. So instead of one quad, you now have 3 quads. First quad will isolate the parent mass of your compound. The second quad in the middle will fragment it into daughter ions, they call them, so fragment ions. And then the third quad will isolate the fragment ions so you can get a good quantitation. So the quantitation mechanism the way to get linear normalized quantitation across multiple molecule classes is that you need to isolate them and look at them individually. You don't want ionization suppression. So more than one ion is hitting the detector, then they'll kind of be an up and down level and won't be linear. But by fragmenting and isolating specific daughter ion fragments, you get what's called an MRN, a multi-reaction monitor transition, which can be used to quantify many compounds at once out of a complex mixture. These instruments like this one will run about 50 hertz, so it can do about 50 different molecules a second if you can get them sensitive enough. And so, but again, you need to know the molecules first, train the instrument on the standards, figure out what their linear fit is, and find their transitions, and then you can go ahead and run. These systems have not just a sample manager, they also have a sample organizer, which takes 96 well plates. So this instrument, the best way to describe it is it's a blind quantitation machine. It looks for the molecule transition you're looking for and quantifies it, and it does it in a large multiplex setting. So you don't really need to do any discovery once you're on here. You're just going really quickly and quantitating. Both MALDI-TOF instruments, it's a completely different beast, right? So the LCMS instruments are nebulized and spraying from like liquid chromatography into the Mass Spec, and this instrument is laser desorption. So it's matrix assisted laser desorption ionization. So you're drying your sample. It has to go into a -8 torr vacuum. So you're drying your sample onto a MALDI plate with a matrix. So it's co-crystallizing inside the matrix. So the laser, the reason you choose different matrices is that they're tuned to the frequency of your laser, or not the frequency, the wavelength of your laser. So the laser in these instruments are 355 lasers. So they're UV absorbing molecules like benzoic acids. And the idea is that it takes in the photons and then transfers them across the band gap to your molecule as excitons, and then will ionize your molecule into the gas phase. You want the laser, so if you just had your molecules and your peptides and things like that on the plate and shot them with a laser, it would just all be transferred as thermal heat, and you would just basically obliterate everything. So some molecules can take the heat and you can just absorb them directly with the laser, but most molecules need some sort of matrix assistance, so it kind of protects your molecules from the ionization, of the energy of the laser, and does kind of like a soft desorption, a soft transfer. And then as soon as you're in the ionized phase, it's the same thing with lenses and optics, and then you're into a time of flight tube through the detector. Both instruments, you have two paths to the detector. You have what's called a linear path. Linear path is low resolution, but you can look at really large molecules like intact proteins and large polymers. And so that would be laser desorption directly up to the detector. Then let's say you have really smaller molecules like peptides and things like that, and you want to get high resolution data for like peptide mapping. If you're doing, you could bounce it. You're basically reflecting it. The gas going out. We don't blow up. Alright, so there's a pusher at the top. So imagine all of your ions are on a waveform, they're moving up through the top space. They're going to get pushed down with a reflector. It's basically like a voltage push to send them back to the detector down there. So it's like doing a V. That turn around that corner, things focus on a turn. So if you have a big enough pusher, you can focus things on a turn. The problem is that pushers can't push anything of any size. There's going to be a limitation. And so on this instrument, it's about 3,000 or 4,000 molecular weight. It's about as strong as our pusher can make things turn without losing all the ions. And then the same thing over here, maybe about 5,000 or 6,000. Pusher's not strong enough to make the turn. And so, since in reflector mode especially, since things of different energies and different sizes can make that turn very differently, MALDI's not really considered a quantitative technique. There's a lot of things going on that are non-quantitative. You can still put in internal standards and try to make it quantitative, but this is it's kind of like a fingerprinting technique, laser desorption ionization. It's also used for what's called MALDI imaging. So you could take a piece of tissue, put it onto a metal slide or a glass slide, and spray it with matrix, put it into the mass spec. So this is like a Venus flytrap leaf right here. And then you can just have the laser shoot at like 20 or 50 micron increments across the entire piece of tissue. And then you can map all the mass spec ions, all the ions that you see, to the tissue. And so you can do what's called mass spec imaging, which is really good for like drug discovery and where drugs go inside animal tissues. Okay, so this is the Zevo QTOF. You guys see this the most in the videos. I like this instrument because it's kind of like the big boy. It's got the quad in the front, and then it's got the same kind of physics as the TOF that was on the MALDI-TOF. So it's a time of flight separation. It's a vacuum tube essentially, and it's just going to send the ions, and it's just mass to the detector. So the time it takes to get to the detector determines how big you are. Faster things, smaller things get to the detector faster, more charged things get to the detector faster, so everything on mass spec is mass overcharged. So you have to account for the charge by looking at the isotope spacing. So you rely on the fact that isotope spacing on the planet is 1, right? Between isotopes is 1. And so if you see a multiply charged peak, you'll see that the spacing gets cut smaller and smaller, and then you can do math and convolution to try to figure out things' actual parent. So what's going on here is you got the same thing where you're electrospraying in, you got the same stack, column managers, sample organizer, quaternary solvent manager, different solvents on top, set custom methods that have already been developed onto the instrument. What's going on here though is you have a couple of unique things that make this instrument better than, let's say, the single quad instrument. First, you have a true waste avert, so you can send a portion of your sample to waste. So typically in some samples you'll have high amounts of sugar like in a soda, high amounts of salt, like you're analyzing like really salty sample. You don't want to send that stuff into your mass spec. It's going to gum up the front source and dirty your instrument. So what we'll do is we'll do a timed waste avert to send those things to waste. Things that don't actually stick to the column will get sent to waste, and then we'll analyze the things that actually stick to the column. And so this is the waste avert right here. And then send the samples into the electrospray. You can look in here and you actually can see the Taylor cone spraying. So that is a liquid spray going down the center
of the needle with a jacket around it where the nitrogen gas that we're generating is being sprayed around the side, and that's nebulizing. Then you'll see here that source cone, that's where the entrance of the ions is. A lot of people will have a gas flow out. You want ionized molecules in there. You do not want gas drop, you don't want water droplets, you don't want anything that's not fully ionized, ready to be analyzed on a waveform, right? You want fully ionized molecules. So the good thing about the Z-spray configuration is that things will go straight down. Where's the, over there. Things that are not ionized at all will just go straight down and not even go into the instrument. Then you're going to come in here, and then there's a countercurrent gas flow, so you have to actually be able to get past that gas flow because you're already an ionized molecule to get into the source. And then it turns again, so it goes down, in, then that direction. And then in this instrument, they have what's called a step wave. So now you're already ionized as a particle and you're coming in, but some things are still either neutral or charged in the wrong polarity. And so there's a voltage potential step. So you're coming in, and then there's an actual lensing step where you have to actually make it up this 6-volt step. So you have to actually be ionized on the waveform and then be moved with the voltage potential in order to make it up that step. So now you know you have only perfectly clean ions going into your quad. And then you're going into your quad. That's where you can do your fragmentation or your sorting and looking at different different ranges of masses. You also can, this is where you're picking up extra charge. So the quad, when it spins things, will give things extra charge. So large protein molecules that are, 100,000 molecular weight can pick up 50 or 60 charges to fit them into the quad range, so you can get high resolution masses on them in the time of flight. And then it's just time of flight to the detector, and you get a nice readout. All right. So this is GCMS. This is a single quad GCMS, right? So it is the low resolution single quad GCMS. They make GC-TOFs, so they make high resolution GC QTOFs. It's actually getting rarer and rarer and harder to find GC-TOFs. We actually been trying to buy them with them, but it's tough to find. They make GC single quads, which is what this is. They make GC triple quads. So everything that I've been telling you about on LC, they do make them on GC. The other cool thing about GC is they have a lot of different ways to get your gas into the instrument. So the difference between a GC instrument and an LC instrument is that's liquid chromatography. All of your separation is being done because of a solid phase media, which a gradient of different solvents are being run across. So it's going from nonpolar to polar. You only can really look at nonpolar molecules on our GCs, but they do make GCs with different column types where you can look at more polar molecules like wax columns. But we run what's called a DB5 column. The DB5 column is a very common mass spec column, mass spec grade column for GCMS of nonpolar compounds. You can't see too many OH groups. You can't see acid groups. You can't see free amines. That will strip the column, and you'll see what's called like a silane background pattern where it's stripping off the siloxanes off of the column material itself. So we're looking at only nonpolars. You can look at polar compounds, but you got to derivatize them first. You got to put like a TMS group or something like that on there, a silane or methyl ester. So there's a lot of derivatization chemistry that goes into GCMS. So then, how does the GC work? It's just baking things off like an oven. So the chromatography on this, it has to do a lot with the media, but it's basically like a 15 to 50 meter long, super long, skinny column inside of a tiny little skinny capillary, and it's just raising the temperature of the oven. And so I go from 40 degrees to 250 degrees, and I bake out the instrument up to 300 degrees. Some of the limitations on GC is that it's hard to get high temperature columns. 350 is about the highest temperature that you can bake off, and that typically relates to about 30 to 35 carbons. So the molecules can't be way too big. But the cool thing is that if you can volatilize it into the gas phase, you can usually analyze it. So then entrance into the GC. So you can put your samples into pentane or hexane or dichloromethane or chloroform, any type of really nonpolar volatile solvent. When choosing your solvent, you want to make sure that it's something that doesn't have any water miscibility. There's a little bit of water in there, it's going to strip the column and make a huge problem for you. So you want really dry solvents. So don't use things like methanol or ethyl acetate because they are some that have water miscibility with. And so the liquid injection samples, you can just do like with my perfume analysis, I just take the sample, dilute it into DCM, and just run it directly. The other way you can take in a sample is you can use headspace. So this is a headspace tube. You can put a sample into the tube. You can then bake the headspace vial to produce gas into certain vapor, and then you can go ahead and grab 500 microliters or so of that gas and put it onto the front of your instrument. And then if you need to concentrate even more, they make something called SPME. So SPME is basically a surface that can bind the molecules in the gas phase, and then you can bake out that SPME fiber and have that go into the instrument. And then finally you can do kind of like a big size SPME, where you can have like a thermal desorption tube, and the tube has a bunch of the sorbate media inside of it, and you can then pass tons of air, liters and liters of air, or like environmental monitoring, tons of air, and bind it onto that sorbate, and then take that sorbate cartridge and put it into a different auto sampler that we have in the other room, and then it would bake that out and put it into the oven. So if you're going to bake out a thermal desorption tube, then you need to have a cold trap on the front of your instrument. So you bake out from one thing, trap it onto the front of the next column, and then bake it out to get your GCMS. So think about everything in this instrument based on temperature, and everything that's sorted and coming off the peaks, not by hydrophobicity anymore, but based on the size of the molecule and how much carbon it contains.